Good morning, everyone. The webinar will officially start in about 2 minutes, so we allow all the participants to join. Good morning, everyone. I think we can officially start today's online workshop. Today's workshop is organized by three sister European projects, DENiM, Project ECOFACT and ENERMAN, and we're organizing this workshop in the framework of the European Sustainable Energy Week. In today's workshop, we will present you holistic management platforms that's to support the energy efficiency in the manufacturing sector, and we will present you the project insights and the case studies provided by the three European projects. I'm Serena Scotton, and I work at Terina Consulting, and I will be today's moderator of the event. Let me change slide and show you today's event agenda. So as you can see, the workshop today will last around 1 hour and a half, and we will have the opportunity to learn more about the ECOFACT project, which will be presented by its project coordinator, Francisco Morentin from the Cardiff Institute. Then we will have the ENERMAN project presentation provided by Andreas Miaudakis from the Sphinx Technology Solution. And then we will conclude with the DENiM project presentation provided by Alan McGivney from Munster Technology University. As you can see, we will have a Q&A session right at the end of this workshop. Therefore, if you may have any questions that you would like to raise to the speaker, please write your queries in the questions chat, and they will be presented to the speakers right at the end of the meeting. And this online workshop is being recorded, therefore the recording of it as well as the project's presentations will be shared with you and with stakeholders right after the project ends, so in the upcoming days. Before diving into each project presentations and into the project details, I just want to spend a few words to give you a sense of the, each project's topic. So as I was saying, all the three projects are EU-funded projects and aims at deploying management platforms to facilitate the manufacturing and the industrial sectors, but from different point of views and with different aspects. For instance, the ECOFACT project aims at supporting the manufacturing industries in optimizing the energy performances of their production systems, but with regards to restrictions such as time and resources. While the ENERMAN project envisions the factories as a living organism that can be that can manage its own energy consumption in an autonomous way. While to concluding, the DENiM project is developing a digital intelligence platform to enable a collaborative approach to the industrial energy management and provides an integrated tool chain to provision the advanced digital services leveraging on IoT, digital twins, digital analytics, and energy modeling. So without further saying from my side, I would like to officially kick off this workshop and dive into more details about all the three projects. And I will leave the floor to the first speaker, so Francisco Morentin, as project coordinator of the ECOFACT project. And Francisco, the floor is yours.
Thank you very much. I think you are about to see my screen. I'm doing the things properly. So, perfectly, let's start. Good morning, everybody. My name is Francisco Morentin. I work for Fundación Cartif, and I'm the project coordinator of the ECOFACT project. ECOFACT stands for Eco Innovative Energy Factory Management System, based on enhanced LCA and LCCA towards resource efficient manufacturing. A very long and friendly name. We will talk about it later. This is a quick overview of the partners of the ECOFACT consortium. So we have 20+1 partners. We have research centers. We have small and medium enterprises. We have 4 big industries. We have, a little bit of everything from very different countries and very different profiles. Okay, so focusing on the main objective of our project is to develop and demonstrate an eco-innovative energy factory management platform based on improved dynamic LCA and LCCA. Okay, so the keywords are factory, of course, and platform. Okay, but also the dynamic LCA. Okay, so our main focus is the effective combination of information and communication technologies for advanced data collection and processing. Okay, so we are somehow a software project, but with a very specific target. Okay, so focusing on the platform that we aim to develop, as all the platforms is going to have levels and components. Okay, and I will talk about it immediately, but we are going to consider 4 levels and several components. Regarding the levels, this is more or less somehow standardized. It's not something we have developed. And from the lower level to the top level, we will have the field level, the edge control level. Then we jump to the next level, which is the data brokerage layer. And finally, on top of that, the applications and services layer. And the ECOFACT platform is going to be implemented on these 2 higher levels. Okay, so focusing on the components, which is the specific develops we are developing and implementing for the project, we have considered several components. Initially, we clusterize these components into 5 types, although with the development of the project, some components are somehow hybrid components between these clusters and cannot be so easily classified. And again, we are considering new components. But from an introduction perspective, we clusterize the components into 5 types: interoperability, operations management, energy aware, environmental aware, and overarching components. Okay, so as a recap of the architecture, at least from the preliminary point we have for demonstration. On top of that, we will have the local data acquisition systems, where the interoperability components are considered. Okay. On top of that, we go to the data broker layer. Okay. And on top of that, we consider the possible components. As mentioned, we consider operations components, energy components, environmental components, and overarching components. Okay. Besides that, we have an initial reference framework activity as usual. So, going into practical details of the architecture we have considered and using a standardized way of representing the components, we have here on the bottom right the local data acquisition system, and as you will see later, we have several local data acquisition platforms or software, as you want to call them. Then we go to the Unifor Edge layer, and we go into the data broker component of the platform. So the component that manages all the data required by the specific components. And on top of that, we have the environmental aware components and the energy and operations or planning components, all the possible specific components. And finally, on top of that, we have the dashboards for the user interface. So at the end, all the information must be presented to the end user of the platform. Okay, so regarding the time implementation, this is the theoretical time implementation. So as mentioned, the first step was the reference framework and methodology definition. And then we have the develop of the specific components in terms of interoperability, energy and operations components, and environmental components development. Have we finished then? According to the planning, yes. Some of them are not finished. We are having some delays with some of them. Others are finished. Okay. After that, in parallel but longer in time, we have to develop the platform and to integrate and communicate the different components. And then we will continue with the demonstration at the demos. And finally, we have the typical horizontal activities of standardization, certification, regulation, replication, exploitation, dissemination, and communication, which are horizontal and all project span activities. So regarding the demonstration activities, we have what we call two pre-demos, which is theme. It's additive manufacturing laboratory in Italy, and we also have another pre-demo, which is in the Fraunhofer EW, has got what they call the E3 research factory. It's not a real factory; it's a research factory for testing mainly automotive manufacturing processes. And we have what we call the 4 demos for real industrial facilities. I'm going to quickly have a overview of them. The first one could be the Arctic washing machine factory in Romania that belongs to the Arcelic Group. It's a really new factory, and it's in the ramp-up phases. They started only having 1 production line, and now they have 2 production lines. Then we have the Athenian brewery indeed in Thessaloniki in Greece. It's the largest brewery in the north of Greece. Then we have the newest and the second factory of the Spanish biscuits manufacturer Ullón, which is located in the north of Spain. It's rather than a biscuit, it's an hybrid factory. It produces classical biscuit references, but also cereal-based products. And finally, we have the car automobile factory of Tofaş in Bursa, in Turkey. It belongs to the Stellantis group, but we are only restricted to the paint shop process since taking into account the whole car manufacturing process would be too wide. So these are the 4 real production facilities where we aim to test the different components of the ECOFACT platform. And now I'm going to start presenting a quick overview of some of the components. As mentioned, there are more components, but I have selected some of them. But we are in my presentation is missing some intermediate or hybrid components that are still under development. So the first component would be in terms of interoperability, the smart data collection by smart sensors and industrial Internet of Things networks. So the idea is to develop and to test an smart sensor prototype to be tested in this case in the EUSEW factory and later in the Arcelic factory, because the idea is to with these solar reference cells to measure the difference in the PV production between two reference cells, one that is cleaned and another one that is not cleaned, and integrate that into the ECOFACT path. Obviously, it has to be tested in factories with PV plants, and that's why it's going to be tested later in the Arcelic factory. Continue with the interoperability components. We have the data acquisition layer for the edge interoperability. If you remember from the general description of the ECOFACT architecture, on the first component that we have is the local data acquisition systems, and we have considered 3 different local platforms for the 4 demos. In the case of Athenian Brewery, the local data acquisition platform is the Artemis. In the case of Pujon is the Smarkia platform, and in the case of Tofas and Arcelic is the constructor power monitoring expert developed by Schneider Electric. So we have 3 different local data acquisition platforms for 4 demos. Regarding the operations components, we have what we call the industrial digital twin, but the industrial digital twin is basically 2 main functionalities. First one is the Autodesk Force digital twin models for the 4 demos, obviously not the 4 lines, not the 4 whole manufacturing processes, some specific lines in the 4 demos, and also is going to help as a web interface for the other tools that we will see immediately after this slide. Regarding the production planning algorithms, we have tested them in discrete event manufacturing processes, specifically in the case of Tofas, the color lotting processes of the cars, and in the case of Arcelic, some sequencing in the washing machine assembly processes. Regarding the energy-aware manufacturing components, we have developed algorithms and in a component focused on industrial energy disaggregation. It has been tested in the 4 demos and in the simple demo, always using offline data. And the idea is through the use of neural networks, being able to predict somehow the energy consumption that a specific process or machine is going to have based on the operation parameters, on the time series of the operation parameters. Regarding the industrial energy flexibility algorithms or components, we have developed 3 specific components depending on the use case to consider. One is what we call is the generation access optimization with fixed demand profile that has been tested in Tofas. The second is the flexibility management with variable demand profile that can only be tested when you have self-energy production systems, in other ways, PV plants. And the final case or use case is the changeover optimization, which has been tested in the case of Athenian Brewery and Guyon in the packaging and in the bottling sections, where when you have to change from one reference to other, you have possible inefficiencies. Okay, jumping into the environmental aware manufacturing, the dynamic LCCA, it's an horizontal and central component tested in all the demos. The idea is to have dynamic models in Sigma Pro, and represents a jump from yearly aggregated LCA calculations to daily or even working shift LCA calculations. And regarding the last, let's say, environmental aware manufacturing, we have a component and use case related with the supply chains collaboration. The idea in this case has been tested in the Arctic washing machine, and the idea has focused around one of the washing machine suppliers, washing machine factory suppliers, in this case the spider arm supplier. So this supplier is going to send by electronic communication the associated specific energy and water consumption to every batch of spider arms that he is sending to the factory. So when this batch of spider arms is used in the manufacturing processes, they are scanned by the working operators, and this allows to assign the specific energy and water consumption for this batch to the specific batch of washing machines that are being produced in that moment. And to finalize with the overarching components, the holistic decision support system will be based on dashboard for the different users and different considered use cases. So it's the screen that the final user will somehow, the first screen that the final user somehow will see. And the idea is that here it will be reporting, alarming, and the global overview to help the end user in the decision support process. And finally, we are also considering cybersecurity mechanisms. Remember the components structure we have. In this case, we are implementing a risk analysis, the safeguards determination, and finally the implementation of the applicable safeguards. I want to emphasize that we don't aim to go further in the cybersecurity. Our idea is that the components that we develop and the platform in general that we develop, it's cyber secure as much as possible according to the actual situation, to the actual standards. So we are not. It's not the main objective of the project, but it's an important issue that cannot be forgotten because it's really critical for the factories. And to finish, this is the summary of our project. We are a consortium from several countries, and you can follow us on our website, on our social media, on Twitter and LinkedIn. And that's all from my side. Thank you very much.
Thank you, Francisco. Thank you very much. So let's move to the second presentation. So Andreas, you can now present the ENERMAN project. The floor is yours.
Thank you, and thank you for your invitation. Let me share. Okay, are you able to see my presentation?
Yes.
Okay. So, good morning to all. My name is Andreas Miaudakis. I work as Chief Networks and Communication Engineer in Sphinx Technology Solution AG. Sphinx is an SME that its main domain is cybersecurity, cyber assurance. With regards to ENERMAN is, as said before, it's a project related to the energy sustainability. And the motivation for this project is the fact that if you see in worldwide literature that the industrial sector use more of the energy produced by more than 54% of the total world's energy, and this is something that we are not overlooked. And taking this as a starting point, if we could introduce an energy sustainability management system that we can achieve a holistic and data-based view of the energy efficiency, energy use and consumption within the factory, therefore to have let's say a life footprint of the energy footprint of the factory. Another point is that the factor of the future, as we go towards Industry 4 and the digitalization of the factory processing, so the factor of the future needs to restate the approach they have on using energy in order to move into a more energy sustainability model, and to do that, that model should have a holistic view on energy consumption. Taking into consideration all these assumptions and facts, ENERMAN introduced energy sustainability as a combination of three aspects. The first thing is the energy that a factory consumes. The second is related to the cost of that energy, and this may be changed due to the power grid price. And last but not least, the environmental impact, the environmental footprint of the factory due to the production process of the consumed energy. Therefore, ENERMAN envisions the factory of the as a living organism that can manage its energy consumption in an autonomous way, and ENERMAN creates a sustainability management framework based on the data collection from the factory, and then holistically process those data to create a dedicated energy sustainability metrics, and then exploiting those metrics and the outcomes of these measurements can be used in order to predict energy trends by modeling industrial processes, and of course taking into consideration the equipment and energy cost, equipment used in the specific process, and specific design energy cost models. ENERMAN has 7 objectives. The first one is more or less what already said: the design of an intelligent, autonomous, flexible, and reconfigurable energy sustainability manufacturer closed loop manager. That is a system that constantly adapts the manufacturing process, product lines, or the functionality of the equipment used in the product lines in a way that the process comply with of the operator determined energy sustainability indicators. Second is this energy sustainability closed loop system should be able to be secure and trusted in order to collect the data from the factory. Therefore, we should provide intelligent, holistic, secure, and trusted data collection and analysis mechanisms that can process energy data from the factory of all actors within the factory, equipment, processes, in order to extract accurate energy sustainability metrics that will be exploited by the sustainability management. The third point is to have a digital twin in order to simulate the factory operation, and based on those simulations to predict in a holistic way based on both real data but also historical data, what has happened in the past, and therefore to predict the factory sustainability fingerprint. And the more important, this digital twin also take into consideration the impact of the human operation behavior. So we take in the human in the loop. We consider the human in the energy sustainability loop in ENERMAN. Therefore, going to objective number 4, we consider throughout the ENERMAN life cycle the human user and operators, and provide extended reality solutions, augmented reality, and virtual reality solution in order to increase the operator's the operator situation awareness on air sustainability, well practice for the industrial processes. Of course, to integrate the ENERMAN various tools, the digital twin, the simulation, the data collection, and so on, in a unified solution, and therefore to realize industrial manufacturing opportunities in energy-consuming environment by validating those tools and techniques in real-world settings. And of course, in order for this to be acceptable, we have to also consider standardization. So to specify standardized regulation framework for sustainability optimization achievement in multiple industry manufacturing environments, and also specify certification strategy for this energy sustainability in the industrial manufacturing domain. And finally, to have a business model and a business plan of how to exploit the outcomes of ENERMAN. And as I said before, the ENERMAN project explores sustainability concept as a three-aspect combination. First is the energy consumption, what energy what is the consumption of energy during a process. Secondly, what will be the cost of this energy consumption, that this cost will fluctuate according to power grid electricity price. And finally, the environmental impact, the CO2 footprint due to the productions of the consuming energy. And by introducing an energy sustainability management system, the ENERMAN project aims to achieve a holistic and data-based view of the energy efficiency, energy use, and consumption within the factory. And to validate the ENERMAN solution, we have the evaluation demonstration of the ENERMAN solution within 3 different pilot categories across Europe. We have 8 different use cases that focus on different energy consumption industrial manufacturing sector, including food, metal processing, and automotive manufacturing. We envision that the ENERMAN solution as a framework that will span throughout the whole design operation continuum of smart factory, industrial manufacturing, in order to make it adaptable to achievable energy sustainability indicators by first predicting the energy consumption that will happen if we change the factory change production lines or the processes, and see what will happen due to those changes. And also to predict the energy and external conditions of the provided energy, for example, due to variation in the energy production market, and taking consideration those indicators to provide autonomously updates on factory production line and with the process control loop to change. That means to change or to schedule the production in such a way that we achieve the maximum optimization with regards to cost and energy consumption. And of course, as I said before, in parallel, ENERMAN system is to train the human operators, the factory users, in order to achieve and to have good practices with regards to energy consumption and, of course, energy sustainability. ENERMAN consortium consists of 21 partners. We have 8 end users with, as said before, 8 separate use cases. We have the technology providers, and we have research and the universities. And with regards to the use cases and the pilots, we have, as said before, 3 main industrial sector. We have a use case with the food industry from Greece, Iotis. We have industrial component manufacturing industry. We have Infineon with regards to chip manufacturing. We have AVL for vehicle testing, and we have CRF, Fiat, for paint, post-processing, bodies of building. And we have also another category on the metal manufacturing process industry. We have Prima additive with regards to laser printing. We have Stomana from Bulgaria with melting process of iron. We have DPS with regards medical device processes, and Asas from Turkey. It's an aluminium industry. And also in this slide, we can see with the arrows there the processes that ENERMAN will be demonstrated to. For example, for Yotis, the process is the chocolate melting process line, or for example, from ESAS is the tri-generation systems. The ENERMAN solution have an architecture that can be categorized in 6 categories. First of all, we have the CPS, the cyberphysical system, which is responsible to collect data from the factory, so it's the data collection system. And then we have the big data analytic engine that is responsible to analyze those data and provide models for the to be used for ENERMAN. We have the intelligent decision support system that provide the decision according to the energy sustainability metrics for the optimization of a specific process. We have the virtual factory where we have the augmented reality that provide training and instruction to the operators in a real-time manner with regards to energy sustainability good practices. We have the simulation prediction engine that used in order to predict what will be the consumption and the energy footprint in the future. And we have the visualization system finally for visualizing all the ENERMAN solution. And if we take a closer look on this description here, I won't dig into much detail, but again here we have the data collection system in the left, and then we collect data and feed the big data analytics. The big data analytics provides model that feeds both the prediction engine, but also to the in order to provide feedback from the visualization system for the virtual factory, and all the components provide the data for the visualization in order for the operator to be able to see what's happening in the system. And of course, big data analytics feed the data also to the intelligent decision support system in order to change, to adapt a process in order to achieve the optimization with regard to sustainability. And of course, this also comes back to the CPS in order to apply the provide solution to the factory. ENERMAN is organized in 5 work packages. We have the work package 1, which is related to the requirements of the ENERMAN system. We have work package 2, which is responsible for the data collection from the factory, also considering the security on this connection of the factory with ENERMAN system. The work package 3, which is related to the industrial management system. So we have the big data analytics, the visualization, and decision engine here. We have the prediction or analysis system analysis prediction in work package 4, which is about the digital twin, the simulation and prediction engine. We have work package 5, which is related to the integration of all those components that are deployed within work package 2, 3, and 4 in order to provide a holistic solution, the ENERMAN framework. And then we have work package 6 that will validate and demonstrate the integrated solution from work package 5. And Vertical to all this, we'll have the work package 7, which is related to communication, dissemination, and impact, but also to standardization, which is important for a system like this that have to deal with real production systems. Also here we have a closer look within the consortium. If you go in more detail of what happening within ENERMAN, work package 1, as I said before, was related to the requirement and of the architecture specification in order to fulfill the use case requirements. Of course, we also took into consideration not only the the requirements with regards to the ENERMAN end user, but also what is the industry needs, to analyze what would be best practice and also existing solution for energy sustainability in other large manufacturing facilities, and of course to draft and define the details architecture in order to implement the ENERMAN solution. With regards to the pilot requirements and the use case specification, we have the requirement definition closer by form of a questionnaire that answered by the end user and so on. Preparation weekly meetings, involvement end user and other partners, and analysis of end user responses. And here again we see in details the use cases that drive this effort. We had the appliance, the first category with regards to appliance and industrial component manufacturing industry, with 3 use case owners. We have the food industry, and finally the metal manufacturing process industry. The second work package 2, was related to the data collection, and again here we realized the edge component that is its job is to collect data from the industrial manufacturer infrastructure within the factory, and this is an intelligent cyber physical system that have functionality to achieve reconfigurability and a real-time response in order to adapt to specific use case. Of course, we created ENERMAN, a software agent in order to collect this data, and this all these were implemented in an edge industrial IoT to support the ENERMAN Flex Control Loop. And of course, all of this will take consideration in order to, in the implementation of the IoT, the security and privacy from these devices in order to be acceptable from the factory.
Sorry, Andres, to interrupt. We are a bit running out of time with the presentation time. Maybe you want to wrap up your presentation, maybe the last minute.
Okay, maybe I'll take 1 or 2 minutes and I will finish. Okay.
Yes, please.
Okay. So with regards to work package 3, here what's happening is to implement all the data analytics in order to provide models and to develop the visualization platform. And also here we're creating VRXR user experience with regards to user training. And of course, here is the realization of the decision engine. With regards to work package 4, here happens the simulation. We have the prediction engine, the risk factor evaluation, taking data from the IoT networks and the decision engine, data analytic engine, and also take into consideration, exploit the energy related indicators to determine the risk of triggering events. Then we have the integration of all those components described before. And finally, we have the demonstration. At the current time, we are still working on the integration, and we start creating the deployment for the pilots in order to deploy also the solution there for the validation of the system. And finally, work package 7 with regards communication, etc. The most important thing for us is here the standardization in order, first of all, to be compliant to standards in order for the ENERMAN to be acceptable by end users, but also to see if our outcomes can be affect any standards. So thank you for your attention. Sorry for the overtime, and be available for questions.
Thank you very much, Andreas. So we can move now to the third and last project presentation. So Alan, the floor is yours, and you can present now the DENiM project.
Thanks, Serena. My screen should be visible now.
Yes, you can see it.
Great. Okay, good morning, everybody. Thanks for joining us today and allowing us the opportunity to share the success of the POF9 projects. My name is Alan McGivney. I'm from the Nimbus Research Centre based in Munster Technological University in Ireland, and I'm the coordinator of the DENiM project. So Andreas gave a good introduction to the motivations of why we're doing these projects, but maybe the focus for DENiM is really around digitalization, and digitalization as a key driver for the green transition. In particular, the integration of digital systems, the management of large amounts of data, the optimization of increasingly complex manufacturing systems are key enablers to create a sustainable industrial sector. So the DENiM project has undertaken this challenge with specific focus on creating value for decision makers, leveraging, I suppose, largely untapped data present in manufacturing systems. So DENiM stands for Digital Intelligence for Collaborative Energy Management in Manufacturing, and it's a 4-year program, and it's a partnership that brings together leading academics and industry partners with expertise in the energy field, but also ICT, and as well as representatives from various industrial sectors from across Europe. The overarching goal really for us is to define and promote the use of best practices across industrial sectors within the EU, and then to support the realization of energy efficient manufacturing systems. As an innovation action, and all the projects are the same, it's critical for us really to show the value of DENiM and these projects in real world conditions. And that's why you see such diverse demonstration sites across the presentation so far today. So to showcase the benefits of DENiM, the project involves 4 complex pilot sites, and these cover different industrial sectors. And these are being used then to evaluate and validate the added value that DENiM can bring to these organizations. And the combination of these pilots then allows us to create a type of community of practice based on diverse industry sectors, with a view then to share lessons learned, establish best practices in relation to energy efficient manufacturing. So across the DENiM pilots, there are some common challenges that we have to address. There are some specific ones as well, but there's been a number of ones that have been identified as common threads that we need to address. And these can translate to many in manufacturing sectors. So they include, disparate and siloed data sets, high energy demands, manual and often kind of reactive interventions that could be limited grid interaction, and obviously, if we're talking about digital technology skills and upskilling with respect to advanced digital technologies is an important aspect of these pilots. So to address these challenges, it kind of requires a very systematic and stepwise approach, and to ensure this we can facilitate, varying maturity levels of the pilots themselves. So as part of this, and along with the other projects presenting here today, we took inspiration from the Connected Factories project, where they approach what they term pathways. So we work together to establish a pathway for energy efficiency, and then the pathway is made up of different levels or milestones that represent then the evolving steps towards the most advanced situation for energy management. So from a DENiM perspective, it's about defining the pathway for energy efficiency through the use of digital technologies. So the main benefits of the pathway is we can use it as an ability to facilitate and stimulate the discussion, and it kind of identify then innovation strategies for company or sector specific scenarios. And also this helps with replication. It allows us to demonstrate how the research and development projects are contributing solutions for future smart manufacturing. And the pathways then allow us to kind of identify and support cross-cutting aspects. So cybersecurity was mentioned, for example, skills, tools, infrastructure. So all of these are common across all of us. So the pathway allows us to align these key enablers and feed it into the different sectors. So our ambition really is to help our pilots move along this pathway towards the most advanced solution using the DENiM platform. So just briefly about DENiM solution is, I suppose the core objective is to develop digital intelligence. So what does that mean? It's about supporting secure and real-time ingestion, contextualization and analysis of performance related data. So with our reliance then on the advanced digital technology, as I said, it's critical for us to support skills development and then consider the legal and ethical implications of the platforms that we're developing. So this includes specific building blocks around data management, model-driven event analysis, decision support for energy management, renewable energy integration, and support the integration with existing and legacy production processes. So DENiM, it's quite ambitious in terms of what we want to achieve within the 4 years of the project, and the project team has been working really hard to make this ambition a reality over the last 2.5 years. So maybe I just provide a little bit more detail and insights of what we've achieved and how we managed to convert these pathways as we define them into practice. So I suppose key to making progress and success of the project is strong collaboration, and that's in the name of DENiM. Collaboration is really important, and having this relationship with our pilot partners allows us to kind of define very specific requirements, goals and ambitions at a site level, and then to convert that into our phase implementation plan. So as part of DENiM, we have 3 implementation phases, or it's 3 main phases that we defined. And this includes, at the first level, achieving integration readiness, so understanding what the pilot needs, what data needs to be collected, how we integrate with it. Then development of the prototype, bringing our tools and components together, deploying them on the site as our P1 first prototype. And then what we're doing now is currently conducting a full prototype evaluation through deployment for the demonstration sites. And the final phase of the project, which will be a little bit ahead of us, is the refinement of these tools, feeding back the outcomes of the evaluation and the services that we develop by DENiM, creating our P2 prototype, which is then our fully fledged digital intelligence platform. A very critical aspect of the project and all the projects that are presented here today is to kind of define an evaluation approach. So how do we know that DENiM has been successful or not? So from a KPI perspective, an analysis was carried out at each of the pilots with kind of workshops to understand what the current availability of these kind of KPIs are, what's desirable from a site perspective, what's feasible, what's viable, and how we can maybe rank the importance of these key performance indicators and understand the impact of each one at the individual sites. So we did this for all our 4 sites, and these workshops really helped us to kind of inform what data needs to be collected via the platform, and particularly then also to help us show our industrial partners what's possible to measure and how we can represent the performance improvements based on the project interventions. Excuse me. So the main KPIs that we kind of focused on are around the environmental indicators, so around inventory, so waste, emissions, material, energy use, and the impact, so the environmental footprint of the products being developed, and the organizational environmental footprint also. Then we looked at the economic and cost indicators, so the ownership cost from CapEx perspective and the OpEx operation perspective, looking at direct and indirect operational and maintenance costs, and also taking into account the cost of the DENiM solution itself. So this figure then kind of demonstrates how we create this overarching online assessment approach for DENiM, and it's a tight coupling between the life cycle analysis and life cycle cost analysis, energy prediction models, digital technologies for data management, and optimization tools for decision support. So the results then of this is kind of a holistic assessment approach that maps across all the 4 pilot scenarios at the different levels of granularity. And then this allows us to demonstrate replicability and scalability of the overall solution. So the first integrated prototype is where we are currently in the project. So as I said, 2.5 years in, and we're kind of deploying and replicating this across all the 4 pilot sites. And with that, so we have a kind of a standard or core DENiM platform, but then we are able to do specific customizations with respect to the models and the services that meet the pilot needs. So, like, without diving too much detail into the architecture, at its most basic level, I suppose the DENiM Digital Intelligence Platform is a data management solution and addresses 4 needs. So there's a need to move from the physical to the digital, so digitization of industrial processes and machining. And then we need to make data integration and interoperability seamless across the different tiers of an organization. And we need to manage and distribute this data effectively to make sure everyone has access to it. And then lastly, we need to use this data to generate knowledge and insight that supports energy-centric decision making. So building on these basic needs, then as a project, we propose a set of abstract functional groups, and this provides kind of a reference system pattern, then, you know, creating like a digital overlay for energy efficient management of manufacturing systems. And we evolved this further then towards the definition of the DENiM functional blocks, or the components as the other projects refer to them as. And this provides then a reference architecture for the development of the DENiM solution. To kind of capture the complexity and modularity excuse me, of the proposed digital intelligence solution allows us then as a project or kind of as solution providers to customize it based on the individual pilot needs, and as developers to allow us to extend it, interchange components, provide new functional blocks, for example, different modeling approaches, different stream layer approaches, without actually compromising the integrity of the overall solution that we want to provide to the end users. Utilizing digital twin is a big part of the project for energy modeling and life cycle assessment. So DENiM will use this then to provide decision support. And this allows end users to integrate energy and sustainability into the decision-making processes and existing business workflows. So this is based on 5 interconnected tools covering aspects of production planning, operational and control, and integration of renewable. So for example, from a planning perspective, we include the development of sustainable production planning user interface or tool, coupled with the LCA and the LCCA analysis. And this allows for reconfiguration, optimization of process parameters, supporting with the objective of being minimizing cost and minimizing the environmental impact. So maybe to give a little bit of a flavor to what we've achieved so far, maybe, and the ambitions of each of the pilots, I'll go through each one and provide a little bit more detail of one in particular. So at our Sidenor CIE plant site, which is based in Spain, this is focused on steel making and the forging process. So this involves then developing both energy and process models as digital twins that can support the optimization of operational parameters towards more efficient processes and enhancing then the existing life cycle cost analysis with online data. So you can see the opportunities there and the targets that we're trying to achieve. And from a first prototype perspective, the first digital models of the electrical arc furnaces and the associated processes have been developed. And we're targeting significant reduction in waste and scrap through the analysis of materials and process optimization. So the next step in this pilot is to link this with real-time models to process parameters and tuning across then the individual steps. The second pilot is at a Gorenje site in Slovenia, and at this site, so there are 2 manufacturers. We're creating a series of digital twins that can be composed together of the specific machining processes, and then this would allow for optimized route planning with energy efficiency as the core criteria around the usage of particular machines across the tool making workflow. So this involves like a significant increase in terms of monitoring to support data collection, and then obviously for the model creation. And a part of this as well is a bit more user engagement to collect the configuration and the planning opportunities that they have at the Gorenje site. Thirdly, our MET pilot is based in Italy. So MET supply critical components for format change and semi-finished product handling, such as large composite screws, bushings, etc. So they're made from diverse composite materials. So this site in particular offers some unique characteristics and challenges for DENiM. For one, I suppose there was very limited visibility of energy performance present at the site. It's an SME, so that they're quite focused on producing their products. And another challenge is that there was no standard process. So each machine operates as a single cell. And although their combination varies continuously, then depending on the desired shapes, mechanical properties, and surface treatments needed for the products. So this was a challenge as well. A focus at this site is really to leverage DENiM to enable the deployment of data-driven models at the edge, so kind of at the cell level, and adding intelligence to legacy machines. So upgrading these with additional sensors and AI algorithms to make better decisions. And this allows for better management then of the assets and reduction of tool wear as well. And the fourth pilot is the wheat synthesis site in Ireland, and the focus of this is on digitalization to support production planning and maximizing the renewable energy and asset management at the site. So just to look a little bit in more detail on this site and to give an example of the demonstration that we have achieved. So if we looked at this site from an operational perspective, underperforming assets and auxiliary services can provide a significant negative impact on the energy efficiency overall. To address this, DENiM is going to provide additional support for asset management. So this can be condition-based monitoring, predictive maintenance, or even use of low-level fault detection systems that can minimize waste, machine failure, and unplanned stoppages in production. So to kind of help with this process, we defined the customer journey with our pilot stakeholders to capture the workflow and map this then back across to the DENiM solution to make sure that we can meet the specific needs. So we began by characterizing the assets along the particular value stream that we're looking at. So it's the poly value stream, and we started with using standalone meters initially just to identify what the most significant energy users, and then we installed more permanent wireless IoT energy meters for kind of non-invasive monitoring of specific machines from an energy perspective. Then we took our reference architecture and we created an on-premise deployment. So on-premise really is the kind of preference for all our pilots, considering the data privacy and security concerns that they all have. The kind of modular architecture that we had defined in the project allowed us then for a very flexible deployment pattern where we can select specific components, specific models and services required for that particular use case scenario. So just to give a little bit of insight into the workflow and the process that we did at this site. So the process began through the provision of an edge connector, which allows us to extract data from the existing building management systems and OSI Pi data store, and to focus on the particular assets that we wanted to look at. From here, the data is then streamed via the core data platform and contextualized in the form of asset operation models, so specific models that incorporate fault detection and diagnosis algorithms. And then this input or the output of this models are fed back into the data platform. So from here, then the outputs can be analyzed by the end user, either through more traditional dashboard representation or analytics frame, or more immersive 3D visualization experience to further contextualize the model outputs as a digital twin used for actionable insights. So this DENiM workflow is being replicated in across all the sites, and we're able to interchange the models that are being used, the visualization modes, and the processes that we're focused on. So it kind of showcases the flexibility of the solution that we're providing. So maybe just to kind of finish up what we've learned over the time, I guess, it's probably clear from the other pilots as well, many industrial sectors kind of experience disruptive changes and are kind of reaping the benefits of Industrial 4.0 innovations, but there are still many challenges and barriers that are hindering the broader uptake of innovative digital solutions. So they range from skills, leadership, technical obstacles, financial and cultural change management. So these are kind of barriers ongoing, but not to be overly negative, I guess there's a lot of positive things that we've learned and that we can take from our piloting experience. There was a real willingness to embrace new technologies and kind of an acceptance of the collective responsibility to create energy efficient and sustainable industrial ecosystems. So to share knowledge and share lessons learned across these sites. So if you want to find out a little bit more about the project, you can join our community through our website. So if you visit our website, you can join as a stakeholder, and we can stay in touch and share innovations in the project. And also you can follow us on our social media channels, or don't hesitate to contact me. My email is on the slides as well if you want to find out a little bit more about the project. So thank you very much for your attention, and that's me.
Thank you very much, Alan. So in the meantime, so we are launching now the Q&A session. So I invite all the participants, if you may have any questions for the speakers, please send your questions in the chat. So in the meantime, just to warm up the Q&A session, I have a question that I would like to address to the entire panel. So it is addressed to all the three projects. So what is the biggest challenge or barrier that you are facing in the deployment of your project, taking into consideration both technical aspects, but also the impact on the stakeholder side? So who would like to start first?
I can start if you want, Serena.
Okay.
I would say in our case is the access to the data, to the monitoring data. It's really complicated because it's not so easy to access the data, because when you realize the data that you require, you find out that in some cases it's not measured, in other cases it's measured but it's not registered, and in the third case is measured, registered, but it's registered in a system that is not connected to any system where you can easily connect somehow. So that's in our experience, I would say that access to the specific monitoring data that you require, because since we are measuring, well, not measuring, optimizing, but you cannot optimize something that you cannot have been able to measure before. Since you are optimizing or measuring the energy efficiency or the resources efficiencies and how it's quite different, the monitoring requirements to control the efficiency of a system than the monitoring requirements just to control the operation of the system per se. That's my point.
Yeah, I would agree with that. I think that was a major challenge for us as well, and the availability of a good amount of data to support the modeling activity, and the thing is quite important and is quite a challenge. Maybe not a technical challenge, but something that we've found quite difficult is staff turnover at the sites. You can lose a lot of knowledge when people leave their roles, so you kind of set up relationships with the pilot stakeholders, and you create these innovations, and you're making good progress, but then whether they move from facilities, they move role, or new people come in, then it's quite difficult again to start that process over again. So it's important for us maybe as projects to ensure the technologies that we develop, that we can some way support knowledge retention at the sites, to allow us then to kind of pick up quickly where we left off, and to kind of keep going, when new people come on board. So skills development and kind of that aspect is very important then as a project.
Okay. Andreas, do you want to comment on this?
You are mute, Andreas, I think.
Yes.
You are still mute, Andreas.
Let me see if I can support somehow. Okay, maybe. Okay, now you are muted. Yes.
Yes. because I got that I was muted by the organizer. Okay, anyway. So for us also, it's the biggest challenge is the data collection for various ways. First of all, we have several use cases, different use cases, so the data are heterogeneous, and we should have some another way to homogenize somehow. So this a challenge, and also of course. It's difficult to access to a real factory where a real process is going on and you have to interfere with it. You have to be very cautious because you can break the process, and it's very serious. And therefore you have to have some kind of isolation. So first of all, we start as a read-only access to the factories. We collected data, or in some cases we had to collect our own sensors in order to collect data. And this of course has the implication that if you use your own sources sensors, then that means you don't have historical data before the installation of your sensors. And secondly, if you have to provide feedback then on the process, it's more difficult because you have to be very serious what you're doing, because you're going to alter an industrial process and you have to know what to do. So again, the interfacing to and from the factory is the most challenging thing. Of course, there are other technical challenges to create the models, to train your model, to have the digital twin, but more or less this is only technical things, while the others also have some policies with regards to security of a factory you have to overcome. And as I said before, this is more intense to us because we have 8 different use cases, so we have to deal with 8 different factories, with 8 different policies on the factory and so on.
Okay, thank you. Thank you all for these for your feedback. Then another question always addressed to the entire panel. So in your presentations, you presented already some pilot case that pilot studies that you are testing, let's say, in your free projects. But apart from the case studies you're already testing in your projects, are there any other type of industries that could be the best candidates for possible replication of your project results in the future? So are there specific type or sector of industries that could be the best candidate? Who would like to?
Okay.
From DENiM?
Okay.
Go ahead, Andrea.
If I may, I think the solution is generic. ENERMAN solution is generic, so it can be applied to any kind of industry, provided that you have a way to optimize its process. Because again, what we are doing is we're creating energy metrics, and then we're trying to modify and predict the modification, what this modification of the process, what impact will have in order to optimize the process. So I think the requirement is that we have a process that can be modified, not a strict process, perhaps by the policy of the organization or by the process itself. And if this is overcome, then of course we can gather data, create models specific for any case, and then provide feedback on the optimization to have the solution for the optimization of the energy consumption.
Yeah, so yeah, I would have a similar kind of take on it as well as Andreas, in terms of the solution is trying to be agnostic of the sector, but obviously you're going to need the domain expertise from a modeling perspective and understanding those processes that we're trying to optimize. So you can view maybe as the solutions that we're providing as enablers to allow any manufacturing sector to consider energy efficiency in their decision-making processes. So I don't think there's a particular sector that would be better than another, but certainly you need to kind of domain expertise from a modeling and optimization standpoint.
Thank you. Francisco, do you want also to comment on this?
Yes, I have maybe a different perspective. Probably because we don't have highly energy intensive demos in our project. I mean, we don't have metal foundries and things like that, which are highly energy consumption points. Specific, usually these production processes are really highly energy consumptive in one very specific point of the manufacturing process. For instance, in foundries, you go to the melting stage, and it's where you have the biggest share of the energy consumption. And in this type of highly energy intensive manufacturing processes, the optimization of these tools, from my perspective, is complicated because changing the manufacturing process is not so simple, because we are talking about really expensive manufacturing machines that usually have paybacks of 20 or 25 years. So once the factory have installed them, it's not so easy that you convince the factory to replace them with a new more efficient technology. And obviously you can use the project to somehow find out the best practices, but usually when you are managing a huge energy consumption in a specific machine, it's not so common that you have best practices on that devices. However, on the other side, if you have industrial processes where the energy consumption is scattered along the factory workshop, then with the help of software, maybe you can find out quicker and with more accuracy where your energy is going, and that could be an advantage versus other type of highly focused energy consumption points. But I repeat, it's based on my experience, because basically we don't have foundries as demos. I guess if we would have a foundry as a demo, things would be completely different.
And maybe to elaborate a little more on what Francisco said, is take an example. You have a process that in order to optimize, for example, the cost of the energy, you can you can start the process when the energy price is low. But in order to be able to do so, first of all, you have to have a process that it does not run 24/7, because if it's always on, you cannot schedule it. And also you have to take into consideration what is the delivery needs of the specific output of the process. So if you have the deadline of the delivery, then you cannot reschedule again to wait for the lowest price energy. So you have factors that can restrict the alternation of a specific process. And a simple example for people to understand is, for example, the energy price. But of course, not only the energy price, it's also the energy consumption, which is more complicated, as Francisco said.
Thank you for your very interesting feedback and replies on this. So we are just about to close the event, but before doing so, I would like to ask to the speakers if there are any further comments that you want to make before closing the event. And yeah.
Well, as usual, and I guess it will be a common request by all the projects, please follow us in our communication channels, whatever you want to follow, I guess, and it will be a common request for all of us.
Yeah, and just thanks for those who attended, and thanks, Rina, for hosting and facilitating the workshop.
Yes, also I'd like to thank you for the invitation. It was nice to see also the other similar project to ENERMAN, what is their approach on the same, let's say, issue. And of course, again, I agree with Francisco. So if you like, you can follow us in our website and social media to get updates on what's happening. And hopefully this project will end at the end of this year. So we'll have more. We have also demonstrators and see the evaluation of how it's going, because till now we're still on the integration phase and we haven't completed one evaluation to see what's the real outcomes of our achievements. Thank you.
Thank you. So indeed, as the speaker said, they showed on the slides the link and the web page where you can connect and see the project's website and social media channels. As I said at the beginning of this event, in the next days, you will receive via email the recording video and also the PowerPoint presentation. So in there, you will have all the details. So if you want to get in contact with the speakers, you can do that and you can follow up with the projects on the dedicated web pages. So with that being said, I would like to thank all the participants for being here today and to having participated in this event. And I would also like to thank the speakers for the very interesting presentations. And again, thank you all and have a nice day. We can officially close the online workshop here. Thank you.
Thank you. Thank you very much.
Bye-bye.
Bye-bye.
Thank you very much. Have a nice day. Bye.
Bye.